Welcome to the last electrical engineering colloquium of the academic years. I'm very happy to have a special guest here today, Eric Yeatman from Imperial College. Let me just say a few words about him, and I look at the long list of achievements and honors that he has received. Just a few data points here. He's actually been a very loyal member of the faculty at Imperial. He has joined them in 1989. And since 2005, he's been professor of microengineering. He's the incoming department head after he's finishing his sabbatical currently in Berkeley. So we were able to get him up here just for about half a day. He has actually a plane to catch at 1:10 today, so we'll have to cut the question and answer session a little bit short at the end of the presentation, make sure that he makes it to Paris tomorrow morning. A few other things that I wanted to mention. So currently he's actually deputy head, becoming the head of the Department of Electric and Electronic Engineering. He's co-director of the Digital Economy Lab, fellow and a silver medalist of the Royal Academy of Engineering and a fellow of IEEE. He's been working on MEMS, microelectromechanical systems, for many years. Also helped start a company called MicroZag, that's looking into micro spectrometers. And currently is very interested in energy harvesting for small portable devices. So I'm very happy to have him here today. Thanks for coming up here, and I'm looking forward to your talk.
Thank you very much, Carl, for the introduction and for the invitation. Thank you all for coming. I think a few of you in the audience know a little bit about energy harvesting, probably others not, but I'm going to give a brief introduction to that as a topic, then tell you a little bit about our own work in the area over the years, and finish off with some thoughts about some possible applications. Do feel free to stick your hand up if you have a question, and of course there'll be a little bit of time at the end for a bit of discussion. So energy harvesting, generally we're talking about creating electricity from ambient sources, and this is something that we've been doing for a long, long time. This is an electrically generating windmill from 1888. And of course now we're generating large amounts of electrical power from ambient sources like wind, tidal energy, and so on, at the large scale. But that's not what I'm here to talk about. The energy harvesting field that I'm involved in is at the micro scale, and I guess the way we would distinguish it from what you call renewable energy is the fact that this is local generation for local use, so portable or embedded devices that generate their own electricity for their own purposes. We're really talking about a miniature scale. And then one other slightly more subtle point is that in the case of motion, almost all electricity that we use is generated by motion in some way or other, whether it's ambient motion or generated by burning fuels. And that motion is usually between a moving part, like a turbine, and an anchored part, anchored to the ground. But in miniature generators, particularly on mobile devices, we often can't anchor one side of the generator to the ground, and this creates an additional challenge, which is one of the things that's typically dealt with in small-scale motion harvesters. And it's usually dealt with in this way. So this is a kind of schematic of what we call an inertial energy harvester, or an inertial generator. And the basic idea is the same as in a conventional generator, which is you have some kind of transducer which makes electricity by transducing the relative motion between two parts. But in this case, one part is the moving part, and the other part, rather than being the ground, is an inertial mass, or a proof mass. So you can see in the diagram, we have the orange proof mass there, which is held in a frame in some way that allows relative motion. It might be a sprung suspension or a sliding suspension. And the frame is attached to something that's moving, so that might be a vibrating machine, or it might be part of your body. And when the frame moves, of course, the inertial mass doesn't want to move because it's got inertia, and therefore you get an internal relative motion, and you can transduce that internal relative motion into electricity. Those of you who work in MEMS or in sensors might recognize that this is the exact same principle that's used in an accelerometer. In the case of accelerometer, you typically have a moving frame, a proof mass, and in that case, the transducer is creating a signal, but in this case, the transducer is using the relative motion to create useful energy that we are then going to use to power something else. So there are several different methods for the transduction part. 3 methods are particularly popular. The most obvious one, I guess, is the electromagnetic one, or the kind of magnet and coil one. This is the basis of almost all large-scale energy generation. It's the effect of a moving magnetic field on a conductor generating a current. And this can be miniaturized and has been, but it's got some challenges and disadvantages when you get to a really small scale. It's really quite a 3-dimensional thing because you need this 3-dimensional coil. As you get smaller and smaller, if you want to keep the number of coil turns up, the coil gauge, wire gauge gets small, and therefore your losses go up because you've got a lot of resistance in the path. And this means the efficiency starts to drop off. And another practical problem is that it starts to get hard to generate significant voltages at a very small scale, partly because of the difficulty of getting large number of coil turns, and also because it's hard to get the motion fast enough because the voltage, of course, depends on the rate of change of flux, which depends on the frequency. And if you can't get the voltage big enough, you can't rectify it, which might be okay for generating a signal for a sensor, but it's not very good for power because we're almost certainly going to want to turn this power into DC so we can do something useful with it, like charge a battery or drive some electronics. So there have been harvesters made this way, but as I say, they tend to be a bit on the larger size, and the ultra-miniaturization of them is not so successful. An area which I'm going to return to a bit later in the talk is piezoelectrics. Piezoelectrics are materials that generate charge separation in response to strain, or the other way around, generate a strain in response to an applied voltage. So if you move a piezoelectric element or squeeze it, you generate a voltage, and this can be used also for transducing in a motion energy harvester. It has the nice advantage that it generates a decent voltage regardless of the frequency of operation. It depends only on the displacement, so we can more easily generate something we can rectify. The main disadvantage is you have to have this relatively exotic piezoelectric material somehow integrated into your device, and that's the smaller you get, the more difficult that gets. If you were to go to a MEMS scale, you have a deposited material. These tend to be materials that have a lot of quirks about their deposition, about their machining, about the kind of processes that have to be used to give them the correct properties. Nevertheless, a very useful system. The final method is electrostatics. This is the common method that's used in accelerometers. So for those of you who aren't familiar with a MEMS accelerometer chip, these are universal devices now. You'll have probably several in your phone and in your car and everywhere else. And the way they work is that the proof mass is on a spring, and you have some kind of capacitance, for example, with interdigitated finger electrodes between the moving mass and the frame or the substrate, so that when there's some acceleration, the capacitance changes and you measure the change in capacitance. Now, if you want to instead use this to generate power, then there are various things you can do. One thing you can do is you can charge the capacitor at the maximum of its capacitance and then disconnect it, let the acceleration pull the plates apart, so you're now doing work against the attractive force between the two plates. That work generates extra energy because it puts the voltage up of the charge that you've just put on the plate. If you now discharge the capacitor at the minimum of capacitance, you get an output pulse which effectively contains that extra energy that you've extracted from the mechanical work. So this was a device we made very early on. I think this was the first ever working MEMS electrostatic harvester. It is a variable capacitor. It's made on 3 layers, as you can see on the right there. The middle layer is the proof mass, which is machined all the way through a wafer of silicon, so about 0.5 millimeter thick. It's on a very soft polyimide suspension, so it moves up and down quite easily, so it can pretty much move at any frequency. The 2 other plates are both glass plates which contain the charging electrodes and the discharging electrodes, and also spacers to set the minimum and maximum capacitance. And so you put a small voltage on when it's at the bottom position, you extract a large voltage at the top position, and any kind of motion makes the plates jump back and forth between the two positions and generates power. And this can work at very low frequencies, which is what you need for body motion, for example, where the frequencies tend to be in the kind of 1-2 hertz kind of range. Quite small amounts of energy, about a couple of microwatts for kind of reasonable motion, which is, you can just about do something useful with that, but it's a bit disappointing for a device that's relatively large. This is about a centimeter square. And there are a number of kind of problems and challenges with this device. One is the silicon is not a very good material for a proof mass because the density isn't very high. It's only 2.5. The range of motion isn't very big because you're moving out of plane, so you get maybe at best 100 micron, couple hundred microns of motion, whereas the maximum energy you can extract is proportional to how far you can move the proof mass internally. You really want to maximize the highest level of capacitance as well as the capacitance range in order to get the most energy out of the system. But making a mechanically variable capacitor with a very large maximum capacitance is actually extremely challenging. You might think, well, it's a parallel plate capacitor. All I've got to do is have a very, very, very small gap at the minimum position. But if you're trying to make a small gap, and I really mean small, like you get down to ones of microns, you're trying to do that across several millimeters, then the amount of flatness that you have to achieve in order to make sure that thing doesn't short itself out is really extremely challenging. It's kind of 1 part in 10,000 of flatness across quite a large area. So this is quite tricky. The minimum capacitance is pretty much limited by parasitics, and you can't really get it below 1 or 2 picofarads. So what you really have to work on is to get the maximum capacitance up. So with all those in mind, those kind of disadvantages, we moved to a kind of different approach, which was to make a hybrid device where the proof mass is no longer part of the MEMS device. The proof mass is now a separate part. So in this early case, which is a kind of proof of principle, the proof mass is a steel pin which rolls across the device. Everything else is done by MEMS-type processing and lithography. So on the substrate, you put the counter electrode, the electrode that doesn't move. You put the spacers, you put the dielectric, you put the charging and discharging studs. Now you have a number of advantages. The mass is quite a bit higher. The motion range is a lot more because it's moving across the device rather than up and down. And you actually get several output pulses per transit rather than just one because you, as you can see by the fingers there, you charge, discharge as you move across. Also, you've not had to machine anything deeply, so all the processing is now simple, low-cost processing. And you can even do the processing now on things like flexible and transparent substrates. So here's a device where the substrate has been curled up a little bit. This also helps to keep the pin in the position you want. And from this, we were able to make a completely self-powered millimeter scale sensor. The test card there at the bottom right, the biggest part is the loop antenna, which is only a bit large because this is a relatively low frequency implementation at 200 megahertz. But if you went to a gigahertz, 2 gigahertz, the antenna would also be at the millimeter scale. Basically, the way this works is, I mentioned before that you have to pre-charge the capacitor in order to give it some attractive force to do work against. So in this case, the pre-charging is done by the sensor element itself. The sensor is the thing at the top right, which is a little tiny electrochemical cell. It's a little pH cell, which generates a voltage which is dependent on the pH of the surroundings. That voltage is placed on the charging contacts of the energy harvester. The energy harvester essentially power amplifies that voltage and dumps the generated charge into a resonant circuit, and the resonant circuit is a radio oscillator. And so every time the rolling pin moves, it transmits a little pulse, and the amplitude of that pulse is proportional to the signal from the sensor. And you can pick that up a few meters away, even though the amount of energy is very tiny. So what you've got now is a self-contained, self-powered wireless sensor with no digital electronics and no energy storage, no battery. It does have a capacitor because it needs a capacitor to make the resonance in the circuit, but not for the purposes of energy storage. So this is quite neat. It's a quite crude device, quite simple. And there's just an example of the transmitted and received signal. So you can see even without any fancy signal processing electronics, it's pretty easy to pick up the signal. It does have, and you can pick up, as you can quite easily in radio, very low pulse energies. It does have a disadvantage, which I'll get back to in a moment, which is that using the amplitude of a received signal as information is not very useful unless you have some kind of calibration reference, because obviously the amplitude is also affected by attenuation, it's affected by the efficiency of your receive antenna and so on. And as I say, I'll tell you the solution to that problem in a moment. But the energy is still pretty tiny, the transmit energy, because these capacitor devices, they can't really get the forces big enough because of the limited capacitance. So we went back to the piezoelectric method, and we thought, how can we use a piezoelectric transducer to generate energy from this kind of structure where you have a non-resonant external proof mass? Trouble with piezoelectrics is that the impedance, the output impedance of a piezoelectric is dominated by capacitance. And so if you want to extract energy from a source efficiently, you want to damp it, you want to load it quite strongly with the electrical load, with the real part of the electrical load. And traditionally, the way to do that would be to put a load which is the electrical, which matches the real part of the electrical output impedance and tunes out the reactive part. In other words, you would put an inductor on the output to tune out the capacitance and then match the real part of the load. The trouble with piezoelectrics at low frequency is that the inductor you would need to tune out the capacitance would be gigantic. The Q of that inductor would be very poor, and so it's basically completely impractical. And so instead, you just put a real load on that matches the magnitude of the overall output impedance. And this means that you're not loading the element very strongly, and that means you really need to let the piezo element run at high Q. In other words, you need to let it vibrate at its own tuned frequency. This means that if you try to excite it directly, you can only excite it at its resonant frequency or very close, and that's not how motion is in most practical applications. You know, the human body doesn't vibrate at 1.00 hertz the whole time. So this has been a big challenge with a lot of work in the literature about piezoelectric energy harvesting, which tends to be beams like this, but with the proof mass directly on the beam, and therefore they can really only harvest at one frequency. So what we do here is we do it in a kind of two-stage approach. We have the moving mass, which is again a rolling steel cylinder, and it actuates a series of transducers with magnets. So there are little tip magnets on each of the beams. As the beam rolls across, it basically plucks the beam by pulling up on the tip magnet and letting go. The beams now can ring down, so they're operating at their tuned resonant frequency, but the proof mass, which is the thing that's responding to the external motion, is not resonant. It'll move at any frequency you like, and it moves at a much lower frequency than the piezo beams. So this is what we think of as a frequency up conversion device, and this allows you to use piezoelectric elements for a broadband harvester, a harvester that can work across a range of mechanical frequencies. Because this is quite a macroscopic proof of concept. To make a smaller device, we'd made another change, which is to move from a linearly moving, unconstrained device, the rolling proof mass, to a rotating proof mass, which is constrained on an axis of rotation. So here we've got a device where the proof mass is a half-circular plate, which is on a shaft. And some of you might recognize that this is exactly the geometry that's used in self-winding wristwatches, and in fact is also used in self-charging electronic wristwatches, and I'll say a bit more about them in a moment. But the mechanism is now very simple. Again, you have a piezoelectric beam. That's the yellow beam illustrated there in the schematic at the top, which is anchored at the top and is free to move at the bottom. The beam, again, has a tip magnet on it, and the proof mass, which is this half circle which swivels back and forth like this when any kind of motion hits it, has another magnet on it which grabs the beam, again, pulls it to one side and lets go, and then the beam rings down at its natural frequency into a load circuit and generates electrical power. So this is nice because the crescent, the proof mass, will respond to any kind of external motion, rotational motion, linear motion, motion in pretty much any direction. It doesn't care about the frequency of the motion, but the piezoelectric beam always moves exactly the same way, exactly the same frequency, exactly the same amplitude. That also makes it quite easy to generate a conversion circuit to turn its output into something useful. So here's a disassembled device, and this was designed to be an exact duplicate of what's used in electronic wristwatches. In fact, we copied the Seiko kinetic device right down to the dimensions of the proof mass, just to show that a piezoelectric approach could do the same thing as the Seiko device and would generate a reasonable amount of power. And you can see from kind of reasonable body motion, the graphs on the right are for different cases of acceleration. So for the most vigorous acceleration, you're generating 20, 30 microwatts, something like that, which is actually quite decent. You can do quite a lot with tens of microwatts. On the other hand, the Seiko device also generates tens of microwatts, so you might think, well, what have you achieved? You've just made something similar to what has been available on the market for 20 years or so. Well, the way the Seiko device works, and I'll show you a schematic of it later in the talk, it's an electromagnetic generator. That's to say it's a coil and magnet generator. And I mentioned before that coil and magnet generators don't work very well when they're miniature at low frequency because the voltage output isn't big enough to rectify. The way that's overcome in the watch is that there's a very high ratio gear train of about 100 to 1 between the moving proof mass and the generator. So this makes the generator move fast enough to be efficient, but as soon as you've got a high ratio gear train, you're now talking about a piece of precision mechanics with a lot of parts which have to be manufactured to very high precision, and a lot of mechanical tolerances in terms of the displacement, which means that the bearing that the proof mass on has to be a very high quality one with very tight tolerances, which means the whole thing is a piece of expensive precision mechanics, and that's why you only find them in high-end watches. Nothing about this device is precision at all. There are no fine tolerances, no precise alignment, no fast-moving parts. In fact, hardly any parts at all. There's the proof mass, which is on a bushing, not a bearing. There's a single piezoelectric beam and a couple of little tiny neodymium magnets, and that's about the whole thing. So this is a way of doing a similar thing, but with a kind of more MEMS micro-integration approach in a way that can be low cost and manufactured at high volume. So marrying two of the things I've talked about already, here's a piezoelectric device with a proof mass. You can just see the proof mass peeking out from behind the green circuit board there. And this is another self-powered sensor, this time with a temperature sensor as its input. And I mentioned before the problem with an amplitude output radio pulse. So in this case, what the output does is it impinges on a varactor, which is put as part of the output radio circuit. So as the sensor voltage changes, the resonant frequency of the radio output changes, and the harvester just dumps energy into that circuit. So now, every time the proof mass swings back and forth, it outputs a pulse. But now, it's not the amplitude, but the frequency of the pulse that depends on the sensor's input. And so there's no longer a calibration problem, and you can see from the plot on the right, you can very easily pick up frequency changes for admittedly quite big temperature changes, but this is just a proof of concept device. And once again, it's a, more centimeter scale than millimeter scale device, but a completely self-powered device without any battery or other energy storage in it. Okay, so that's some of the work we've been doing. Let's like a little sort of change of pace now. Here's something that most of you are from the EE department here, so you're probably familiar with this, but it doesn't hurt to quickly review it. We live in a technological world that occupies very many orders of magnitude of electrical power. From at the top, the total electrical generating capacity of the world, this number is probably a little bit out of date, but it's in the several terawatts regime, so a few times 10 to the 12 of watts. A typical large electrical generating station is about 10 to the 9, a gigawatt or so. I'm just taking sort of orders of magnitude here. Your house, or a typical house, at least in America, probably has at least a capacity, if not an average consumption, of 10 kilowatts or so. A person, I know it's not an electrical device, but a resting person is consuming about 100 watts of power, obviously generated by the food you eat. When you exercise vigorously, or running, or cycling, or something, that might go as high as 400 or 500 watts, but 100 watts is just sleeping or sitting in an armchair, keeping your body warm and keeping your brain operating. Your laptop, maybe 10, 20 watts or so when it's fully functioning. Your heart is similar kind of energy level. Your cell phone, when transmitting, is in the ones of watts range. So we're already down 12 orders of magnitude. Keep going down. Wireless sensor. Okay, so this is something that I'm going to talk about a bit more. There's not really a particular power level for a wireless sensor. It depends an awful lot on what it is you're trying to sense, how far you want to send that message, how often you want to make the measurement. But as a kind of crude ballpark, I think a milliwatt or 1/10 of a milliwatt or so is probably reasonable. Your electronic wristwatch consumes about 1 or 2 microwatts of power. That includes the electronics and the mechanism to move the hands around. The reason the electronics are so low power is because the clock rate is very, very low. There's very little computation going on in your wristwatch. The amount of signal you need to receive a decent cell phone signal, now we're getting into nanowatts or even sub-nanowatts range. So from your cell phone signal to the world's generating capacity, 21 orders of magnitude of electricity. Now, one of the reasons for saying this is that those devices that I've been showing you, which generate, in some cases, a couple of microwatts, in other cases, maybe a few hundred microwatts, or even milliwatts, they're not going to solve this problem at the top. We would have to make like 10 to the 14 of them or something to replace big power stations. But they can do other things. They can indirectly do something about the world's energy capacity. And the main reason, the main way in which they can do that is to make this wireless sensing, ubiquitous sensing paradigm effective. But before I talk more about that, let's just say a little bit about how much energy you could ultimately achieve from inertial energy harvesters, because this is something that people working in this field get asked constantly, and everybody says, oh, can I put one in my phone and I won't have to charge my phone up anymore? Well, you can work out some limit based on some very simple Newtonian mechanics. You simply say, my transducer is applying a force on my proof mass. The proof mass has got a kind of virtual force of its own mass times the external acceleration. So if my transducer force is bigger than that, the internal motion will seize up. I'll stop the proof mass from moving, and therefore clearly nothing's going to happen anymore. So my maximum force is ma. The work you can do with ma with an internal displacement of delta z is clearly just the work times the force times the distance. And if you do that twice per cycle, once in each direction, then you get a maximum power, which depends only on 4 things: the mass and the displacement, internal displacement range of the proof mass, and the acceleration and frequency of the external motion that's causing it to move. This is what that looks like in actual numbers. I'm concentrating on the very low frequency end now, so things like body motion and some kinds of big structure motion. So if you're doing machine motion, you might move up into the hundreds of hertz, and then the numbers get quite a bit bigger. Because it's the proof mass times the displacement, it actually scales as volume to the 4/3. So as you get smaller and smaller, the power density unfortunately drops a little bit. And this means that probably below a cubic millimeter or so, you're never really going to be able to do anything useful. But in the range, cubic millimeter to a cubic centimeter, I think you can do something useful. And in this graph, so I've got 2 lines, one for 1 hertz and one for 10 hertz, as the black and the purple band. And on it, I've put a few devices, in this case, their size and their power requirement. So up at the top, you've got the blue diamond, which is the laptop. Okay, it wants 10 or 20 watts. It's maybe a few hundred cc in size. So it looks like to power the laptop, or in the next case along the cell phone, you pretty well need a harvester of similar size to the device, and the motion needs to be operating for a similar amount of time to the time you want to use the device. You can sort of see immediately that's, especially for the laptop, it's not very realistic. I mean, if you carry your laptop with you when jogging and you only use it for 10 minutes a day, then you're probably going to be just about okay, but that's probably not realistic for most people. On the other hand, the wristwatch in green is orders of magnitude below the possibility of harvester. That's why it's kind of low-hanging fruit for this application and has been commercialized already for a long time now. Sensor nodes also looking pretty good. You know, a cubic centimeter or something that draws 100 microwatts, which is pretty good for even for a commercial sensor, within 2 orders of magnitude below what's theoretically possible for a harvester. Now, harvesters that people have made have been at best about 5% of the theoretical maximum. So we have a ways to go really to get towards those blue and purple lines. But you know, that's looking like a realistic application. The other thing, though, you've got to compare besides the application is the alternative. And the alternative, I forgot about this slide. So flip back through a thought for a moment. How much do you really need to power a sensor? Well, a sensor has to do 3 things usually. It has to sense, it has to do some kind of signal processing, digitization, and so on with an internal circuit, and then it has to transmit by radio its signal to somewhere. There are already some very low power sensors on the market. This is a commercial 3-axis accelerometer, 2 microamps, even when measuring at 100 samples per second. This is extremely impressive for a commercial device. The device on the right is not commercial, but then again, it's not totally up to date. But this shows that even something you would think of as being very high power, which is video imaging, can also be done in the microwatts kind of regime. So we're talking about being able to do some pretty sophisticated sensing at microwatt power levels. And the processing also, there are now processors available in the same kind of range. And radios, you know, the rest power of radios is well below a microwatt, and even the transmit power for short distances is coming down. So 100 microwatts for a complete wireless sensor is actually pretty easy now. 10 microwatts is within the range, I think, of commercial technology, probably within the next couple of years. 1 microwatt, definitely achievable. No major theoretical barrier to doing that. But I mentioned before the competition. The competition, of course, is batteries. Most wireless sensing and other wireless devices are powered by batteries now, as you know, and you all plug them in when you get home at night to charge them up. Batteries are energy devices, not power devices. So if we want to compare a harvester to a battery, we've got to say how long we want the battery to last for so that we can work out its average power potential. I've assumed here lithium batteries, which are probably the best in terms of energy density. And I've taken 2 cases in the green dashed and purple dashed lines, a battery that we need to last for a month and a battery that we need to last for a year. Obviously, if we need it to last for a year, its average power output is going to be that much less. I've assumed that the battery energy is proportional to volume. That's not quite true because as you get smaller, peripheral parts of the battery, like the electrodes and the casing and so on, take up a larger and larger proportion of its total volume. So that actually means the battery is worse than I've indicated there. But what it shows you is that, first of all, harvesters win out in the kind of 1 cubic centimeter, 1/10 of a cubic centimeter to a few cubic centimeters range. They start to do quite poorly in the cubic millimeter range. And they also really win if you need an application where you need months or at least weeks of life. If you're happy to recharge your battery every day, then of course the battery powers move up by another factor of 30 from the green line, and now the battery pretty much wins all the time. So we want applications where daily battery charging or replacement is unrealistic, and there are a lot of applications like that. Before I get on to the applications, which is the final part of the talk, I'm just going to mention a couple of other energy harvesting topics that we've done in the group. This is a completely different kind of motion energy harvesting, a micro wind turbine. This is a turbine with about a 2 centimeter outside diameter, including the cowling. And it's made with a silicon laser micromachined turbine blade and an internal axial flux electromagnetic generator. And this is the kind of thing you might put, let's say, in an air conditioning duct or in a ventilation shaft or something like this. Produces a few milliwatts for a few meters per second of air motion, which is the kind of airspeed you'd expect in that kind of application. And this could again be for making, for example, powering an air quality sensor or something like that. So quite a bit more power than the vibration harvesters, although, as you can see, quite a bit more sophisticated device. The key thing to making small turbines work effectively is that they have to turn very fast. And this means that making good quality bearings is probably the key issue about really making this technology work well. It's a bit more about how you can see the flat coils and the embedded magnets for the axial flux generator part. And there's some things about the power output. So you can see the power output is getting up to, say, 3 milliwatts or so for wind speeds of 8 to 10 meters per second at about 3,000 RPM. This is the kind of concept of application. So you might have a sensor array, as I said, in a big airflow duct, maybe the air handling duct in a clean room or something, I don't know. And if you want a kind of permanent sensor, let's say for safety monitoring, where you don't have to worry about climbing into the duct and changing the battery, then this is a potential way of doing it. This is a completely different application. It's not motion at all, so it's slightly off the title of the topic, although there is a link. This is a thermoelectric harvester which we developed for Airbus to do aircraft structural health monitoring. This is strain monitoring inside the wings or inside the structural parts of the aircraft. And it uses a commercially available thermoelectric generating cell. So what's different about it is that usually thermoelectric generation depends on a temperature difference in space, for example, between a hot, like an exhaust system, and a cold thing like a heat sink. This device uses temperature change in time rather than in space. And what you take advantage of is the fact that apart from the heated cabin, the temperature in the rest of the aircraft is at kind of ambient temperature when it's on the ground, and at very low temperature, maybe minus 40, minus 60 C, or even less, when it's in the air. And so what we want to do in order to turn that into a temperature difference across the thermoelectric generator is delay the temperature change on one side only of the TEG. And this is a bit like the inertial mechanical harvester. You need some inertia, only in this case it's thermal inertia on one side. Now thermal inertia could be just a thermal mass, like a big block of metal, but what's even better is something that undergoes a phase change, like water, for example. So the way this device works is as a small water cell, or aqueous solution cell, which is obviously melted when the aircraft is on the ground. As the aircraft takes off, the temperature drops quickly well below zero on the lower ambient side of the TEG, but the temperature on the top is stuck at zero until the whole cell freezes, and this takes about 20 minutes or so. Meanwhile, you have a big temperature difference across the TEG, which generates power continuously. Then eventually the water freezes, the electricity stops, but now you're going to land. So now the temperature warms up on the ambient side. The top side is still stuck at zero because it now has to melt, and then you get another cycle of 15 or 20 minutes of power generation. You can see that all happening on the graph at the bottom. The reason the takeoff one is divided into two is some complicated thing about the way the water freezes, which I won't go into at the moment. But you actually get enough out of this. You can see the size compared to the pound coin there to power about 10 to 20 milliwatts instantaneous power of strain sensing in cyclic operation for the whole of the flight. And again, no permanent battery storage. There is a buffer storage because you have to smooth out the energy that you generate so that you can power things continuously. People in aircraft, they've got already far too many wires, far too much cabling in the aircraft. They don't want to add any more. It's heavy, it's complicated. So the idea that they can start to make some things wirelessly is great, and clearly you don't want to have batteries embedded inside the wings of aircraft where somebody has to crawl in and try to replace them or recharge them somehow. A bit of a specialist application, but it shows you that there's some interesting things you can do in these sensing applications. There's the whole device, which includes the electronics for the strain sensor, the radio, and this, unlike the little motion-powered sensors I showed you before, this does have conventional electronics, has a microprocessor, uses a conventional radio set, has security on it, and everything like that. And one final little topic, which is actively supplying electricity. I know there are a number of people in this department working on electromagnetic, both inductive and radio frequency methods of supplying power wirelessly to various kinds of devices. You can also do that by sound, and particularly for sensors embedded, for example, in the human body, ultrasound has some advantages. It can be much more directional because you can get very small wavelengths easily. This is a MEMS device we made which creates mechanical actuation by receiving an ultrasonic beam, and converting the vibration of a diaphragm in response to that ultrasonic energy into a mechanical vibration of some MEMS parts, and then that in turn is rectified by a kind of scratch drive actuation to move a part mechanically. And this is, I think, quite early work on this topic, but I think delivering power as well as signals by ultrasound is quite an interesting way of powering something that you can't get at easily. Okay, so I said I would finish off with a little bit of thought about applications. Energy harvesting, particularly motion energy harvesting, is not very widely applied yet. There are some commercial applications, but mostly smaller niche applications like the watch I mentioned and a few others. So what's the killer app that's going to make this ubiquitous and create the huge companies? Well, this is one that's been talked about a lot, tire pressure sensors. There was a lot of hope in this area maybe 5 to 10 years ago, because it's an application which is very widespread, it's mandated by law, it's not easy to get the electricity from the car into the tire, and there's a lot of motion. So far, energy harvesting hasn't won this battle. Batteries are still winning. One of the difficulties is that at the rim of the tire, the centrifugal forces, mechanical forces, get very large, into the hundreds of G, as much as 1,000 G. And making a device with moving mechanical parts that doesn't get completely stuck because of this huge centrifugal force radially outwards is extremely difficult. And I think this is one of the reasons why the vibrating devices aren't winning this battle yet. The watches I mentioned already, they work very well. I think the trick is to come up with something, as we've been working on, which makes them so cheap and readily available. Of course, watches are becoming quite a hot thing again because people want to put a lot more functionality, and indeed have done, into a watch. I think if you look at the new Apple Watch, its power consumption is going to be too high for energy harvesting because it's got probably too much functionality on it. But there'll be something in between, which might be eternally powered by a harvester, which would mean you'd have a watch you wouldn't have to recharge, which I think would be quite nice. That would have some electronics on it and would still be cheap. Implanted medical devices, of course, is a great kind of future application area for all this kind of technology. It's a challenging one because, of course, the reliability has to be very, very high. You have to go through very, very long cycles of qualification in order to ensure its safety and reliability and so on. You'll have already seen, and probably some of you are wearing, personal health electronic monitors like Fitbit, that kind of thing. I think both for the electronics and the power sources and other aspects of that technology and the radios, personal health is a great first step towards a truly medical device because it has a lot of the same functionality, but because it's not a really medical device, it doesn't have the same qualification requirements, it doesn't have the same litigation issues, it doesn't have the same licensing requirements. So it's a kind of partial step through that door. I think as the personal health devices get more developed, they will be a bridge into truly medical devices. And really, we want to limit the number of batteries we put inside people's bodies. It's a nuisance to recharge them. It's a great effort to replace them. And if we can find better ways of powering these kind of devices, I think that would be a great thing. I mentioned the Airbus application. I think smart maintenance of sophisticated industrial machinery is becoming more and more important. Some of you may know about the change in the Rolls-Royce business model. You may know that Rolls-Royce is not a luxury car company anymore, but they are one of the two big manufacturers of aircraft engines. And they are no longer selling aircraft engines to airlines. They now sell basically horsepower hours. So they maintain ownership of the engine. The airlines pay according to usage. And this means that the reliability and uptime and maintenance is much more of a concern from the manufacturer than it used to be, because now it's a way for them to lose money rather than to earn money. And so they have a lot of sensing in these devices, and actually Rolls-Royce headquarters are receiving data from all their various engines that are flying on different airlines all around the world in real time, constantly. I think this model will spread to more and more industries because we can make a lot better use of expensive machinery. We can reduce the downtime for maintenance, we can increase the lifetime, and we can reduce the maintenance costs by making maintenance smart, replacing parts when they really need to be, rather than because they've gone through some kind of 5,000 hour service life, and that's the standard that you have to tear something down. But the final application, of course, is this wonderful Internet of Things that everybody talks about, and we've already passed, this is a Cisco graph, we passed the point where there are more things connected to the Internet than there are people on Earth already a number of years ago, and we're now at multiples of that, so tens of billions of things connected to the Internet. And people talk about 1 trillion sensors and so on and so forth. Well, maybe we're going to have 1 trillion sensors, but are we going to have 1 trillion batteries? I really can't see the world recharging 1 trillion batteries every night. So if that's going to happen, we've got to find other ways of dealing with the power requirement. The most developed harvesting method is solar, of course, and a lot of applications that's perfectly suitable, but many others, like embedded devices and implanted devices, there isn't any light, so we can't use that. As far as motion goes, well, not everything moves, so not everything is suitable for motion harvesting. But if we're going to put intelligence in everything, just think of the number of ordinary objects in our lives which move and which we would like to add more intelligence to. For example, livestock. Livestock are pretty well all electronically tagged already, but usually with passive tags just so you can track, for example, their motion through a gate, through a milking gate or something like this. If we could power up those tags, we could measure more things about their activities and do more monitoring of kind of active management of livestock herds. Luggage. Everybody wants to know where their luggage is, but maybe they'd also like to know what kind of rough handling their luggage has had if they find something is broken. Same thing goes for packages and mail, of which there are trillions of pieces circulating around the world at any one time. And then also simpler, cheaper things like toys, tools, sports equipment. Now, these are all things that we expect to buy for a small amount of money, put in a drawer, and if we take them out 2 or 3 years later, we expect them to work. We don't expect to discover that the electronics are dead and therefore they're unusable, or we have to plug them into some charger that we can no longer find. If you're going to put intelligence into everyday household items like this, it better be completely maintenance-free and completely reliable, otherwise people aren't going to want it. And I think the only way to do that is to make them self-powered, perpetually powered in some way or other. So I think there are a lot of opportunities. There's still a lot of technical challenges, but I think it's a field that has a lot of future in it. Thank you very much.
So thanks very much for the great presentation. I think we have a few minutes for question and answer. So any questions in the audience?
You mentioned, you have, I mean, it's a very nice graph you have on the power versus the size. Another one, class of the antenna harvesting, like RF, right? Harvest.
Yeah, so I didn't talk about that.
Similar graphs, you know, things like that compared to it.
So I used, for size, I used volume, because volume is the crucial thing for inertial energy harvesters. For RF harvesting, I think the crucial thing is the size of the antenna. And so that's maybe the linear dimension rather than the volume. You can make a very long, thin device. And it obviously depends on what frequency range you're trying to harvest. The lower frequencies you're aiming to capture, the longer the antenna you need in order to capture those efficiently. Now, more and more high frequency RF is getting into the atmosphere. People are doing 60 gigahertz stuff, you know, and 75 gigahertz stuff for kind of low-cost radar. I think miniature devices for harvesting those kind of frequencies are going to be pretty good. But at the moment, we've got very little of that, so we're having to harvest kind of 1 or 2 gigahertz stuff from cellular systems and even lower frequencies from kind of TV transmission. Then it's down to antenna size, really. And then I think you're talking about multi-centimeter, even tens of centimeters to really do it well. If you can run a wire up something, the rest of the device can be very, very small. Yeah.
Is there any capsule we can like swallow in and continue circulating out for other vessels?
Yeah, so this little device that I showed you was the sort of early electrostatic self-powered harvester, this guy here. I think one of the ideas, and this is why it's a pH meter, was that you could potentially swallow this and it would circulate not in your blood, but in your digestive system, and you could get a radio signal for your blood acid, for your stomach acid level, for example. And then you would just, you know, excrete it along with the rest of the waste. And this is already at a size which is pretty much suitable for that application. To get into your bloodstream, then of course you've got to go even a smaller size down, and then there are many safety concerns. But in principle, I think it's a possibility. Yeah. The other interesting thing about the digestive system is, of course, is to take images, you know, and there are already video camera capsules that you can swallow, and they're a bit big for swallowing, but you can, and they are more power hungry because they've got to have a light source and a video. And I think they're externally powered, some of them, and some of them just carry a battery that lasts. That would be another area where if we can miniaturize it further to power it by harvesting would be quite nice.
See, I had a question too. So you gave an equation for the theoretical limit or maximum energy that you could extract, and then I think you also mentioned that the current efficiency that you get is much lower. I forgot the exact number, but it was a few percent. So, so what are the limitations right now, and then where do you think this will go in the next years? Are we ever getting up to, I don't know, 50% or anywhere close to that?
I don't see any reason why we can't get sort of 30, 40, 50%. I mean, like anything, once you get beyond that, you really start to push it more and more difficult problems. And you've got to think about, is it the end-to-end efficiency, including the power processing electronics, right? Because you have this problem of turning often a weird signal like a piezoelectric pulse into some nice DC that you can charge a battery with. And making rectification and voltage transformation efficient gets more and more difficult as the voltages get smaller and as the kind of parasitics get more and more influential. This is an area where there's a lot of progress being made, actually. So you can now buy two companies, Texas Instruments and one other, produce a kind of energy harvesting rectification chip in a little integrated circuit, which is actually quite efficient.
So that's quite low voltage. That's at the moment the main bottleneck where most of the losses are, or?
No, I think also at the moment the electromechanical parts are generally not as good as they could be. Yeah. I think in the case of the piezo, it's this problem about bandwidth. In the case of electrostatic devices, this problem about not getting the capacitances high enough. In the case of each transduction method has its own different problem that people are struggling with.
If there are no more questions, then
I've had a long term, and
I'd like to give you a chance to catch your plane, but I want to thank you one more time for the great presentation.
Thank you.
Right.
Thank you very much
for coming. That's it for this year. We'll see you again in autumn.